All right, everyone, welcome back. So, the first thing that we're going to talk about this trimester is energy. I'm going to go over today a few of the different types of energy and give you a couple equations to work with. Later, we're going to be talking about conservation of energy and how things gain or lose energy. So, energy in general can be kind of divided into two different types of forms. We have kinetic energy and potential energy. Now, kinetic energy, you can see in the left hand column here, we have mechanical energy, electrical energy, thermal energy, radiant energy, sound energy. So, you might think to yourself, like mechanical energy, it's energy due to motion of an object. Here you can see kinetic energy is energy of motion. So that makes sense. But when we look down here, you think electrical energy, thermal energy, radiant energy, sound energy. How is that the energy of motion? Now, what we get here is that we actually have little molecules or little elements that are actually moving. So, thermal energy, radiant energy, the faster those little molecules are vibrating, the hotter something is. Electrical energy, we really have current that's flowing through a wire or something like that. And current is just the movement of electrons. So, that's also a type of kinetic energy. Sound energy is vibrations in different particles to transfer that sound energy. So it could be vibrations of the air molecules or of water molecules or whatever the medium is that we're talking about. Potential energy over here is stored energy. So that's energy that's going to be stored for later use. Today we'll be talking about mostly these two, gravitational energy and elastic energy, but you also have chemical and nuclear energy as well. So, the first thing we're going to be talking about today is potential energy. So, an object may store energy by virtue of its position. So, if we look over here, we have this demolition wrecking ball. Now, I'm going to have that Miley Cyrus song stuck in my head. But it's up at a certain height. So, it has energy that's stored. This arrow right here, this guy pulls back the arrow, and because of that position of the bow, that arrow has stored energy. So, energy that's stored and held in what we call readiness is called potential energy because the stored state has what we call the potential to do work. Now, we haven't really talked about work yet this trimester, but that is something that we're going to be talking about in the next couple weeks. When we have this wrecking ball up at a certain height, it can then swing down and actually knock down buildings and things like that. So, it has the potential to do work, and we'll talk about that more later. So three types of potential energy. Really, there's kind of four, but we can kind of lump nuclear and chemical kind of together. There's elastic potential energy, chemical potential energy, and gravitational potential energy. Now, we're going to be talking about mostly elastic and gravitational potential energy. This elastic, when you think about that word, you think about rubber bands and springs and something like maybe a bow and arrow, right? This is kind of elastic as he pulls back that bow. So that's stored energy with an elastic material. Chemical potential energy is the potential energy that's stored in chemical bonds. So when you eat something, you eat an apple, or I don't know, you eat something, right? And then that energy that's in the components in that apple or a protein bar or something like that can then feed your body. Your body breaks it down, uses it, you have chemical reactions in your body to convert it to ATP and energy within your body. So that's what chemical potential energy is. And then gravitational potential energy is something like this wrecking ball. When it's up at a certain height, it has gravitational potential energy. So let's talk about gravitational potential energy first. Gravitational potential energy is the potential energy due to elevated positions. So whenever something is up at a certain height, it has gravitational potential energy. The higher the height, the more gravitational potential energy an object has. Now, for this, we do need a reference point, and usually what we say is that the reference point is the ground, meaning that our x equals 0 or h equals 0 is the ground. So if I take a pencil and I put it 1 meter off the ground, my h in the equation that I'm going to teach you next is just 1 meter. because we know that h is really our delta x, right? Our displacement. And so we have to have some x equals 0 point. Now the unit for energy, and this goes for this goes for kinetic energy as well and elastic potential energy when we talk about those. The unit that we use for energy is a capital J, and it's called a joule. So our equation for gravitational potential energy is potential energy equals m times g, little g, times h, where m is the object's mass in kilograms, g is the acceleration of gravity, which we know is 9.8 meters per second squared, and h is the height in meters. So let's do an example. We have a 70-kilogram base jumper stands at the top of the Eiger Mountain in Switzerland. If the Eiger is 3,970 meters tall, how much potential energy does the base jumper have at the top? This picture right here is not in Switzerland. I just randomly found this picture, but I made this problem up because my husband and I were in Switzerland last summer, and there was literally people base jumping off the mountains like in the morning. It was crazy. Anyway, I would never do that. People are crazy. So first and foremost, let's write down our givens. So our givens here, we first have that the base jumper is 70 kilograms. So we can write down the mass of the base jumper is 70 kilograms. The Eiger Mountain, it says, is 3,970 meters tall. So what they're giving us there is the height, or h. So h is equal to 3,970 meters. And then we want to know the potential energy. So I like to put potential energy equals question mark. So now we want to write down our equation. We get potential energy equals mass times acceleration of gravity times height. We plug in our numbers. M is 70, H is 3,970, and then we know G is 9.8. So we can plug in those numbers here and then just multiply them all together. 70 times 9.8 times 3,970. We get a potential energy of, what is that? Man, that's like 2,723,420 joules. Now, that's a really big number. Because it's so big, what we can do is we can divide that number by 1,000 and we can get the number in kilojoules. So just like grams to kilograms, we're just converting to a number that's a little bit more manageable. So if we divide this by 1,000, we get the potential energy is 2,723.4 kilojoules. All right, so let's talk about elastic potential energy. Now, when we have a spring that's stretched or compressed, it has stored energy. We know that, like down here, if we stretch this spring right here, or if we compress that spring, it's just going to bounce back to what we call the equilibrium position. So it's the relaxed state. This is called the equilibrium position. It wants to go back to that position, right? So it has stored energy in both the stretched position and the compressed position. Now, the equation for this is elastic potential energy is equal to 1/2 times K times X squared, where K is the spring constant, and the unit for that is newtons per meter. Spring constant, we talked a little bit about this when we talked about Hooke's law, if you guys remember that from Newton's laws back in the day. It's the spring force equation. K is, every spring has a spring constant. The stiffer the spring is, the higher the K value, or the spring constant value. You'll see values ranging from like 20 to like 2,000. So they can be really big sometimes. All right. So don't be alarmed if you get a K that's really big. And then X is going to be the distance the spring is stretched or compressed from the equilibrium position. So like I said, this is the equilibrium position right here. If we stretch this spring to here, our X value in this equation will be from that equilibrium position to the stretched position. So this right here will be our X value. All right, so our second example, we have when a spring is stretched 20 centimeters from its equilibrium position, it holds 50 joules of potential energy. What is the spring constant K of the spring? So again, let's write down our givens. we know that it says a spring is stretched 20 centimeters. So this right here is the amount of stretch, or our x in that equation. Now, can we use 20 centimeters? I hope you said no. What do we use in physics instead of centimeters? Yes. Right. Yes, we have to use meters, not centimeters. So we need to convert this to meters before we can plug it into our equation. So our first given is our x, which is 20 centimeters, which when we convert, it's 0.2 meters. So remember that. It has to be in meters, not centimeters. So you have to remember to convert. And then it says it holds 50 joules of potential energy. So that's our second given, is that the potential energy is 50 joules. Now we want to know the spring constant K of the spring. So now we want to write down our equation. We have the potential energy in the spring is equal to 1/2 times K, our spring constant, times X squared. Now we can plug in our numbers. We know that this potential energy here is 50 joules. We also know that X right here is 0.2 meters. And then this is what we're solving for here. So plugging in our numbers, we get 50 joules is equal to 1/2 times K times 0.2 squared. The first thing I'm going to do here is I'm going to multiply both sides of this equation by 2 to get rid of this 1/2 right here. So I get 100 equals K times 0.2 squared. We're then going to square that 0.2. Be very careful here. You want to do this into your calculator, because when you square 0.2, you get 0.04. Some people just want to try to do this in their head and they put 0.4 instead of 0.04. So just be really careful about that. And then from here, we just want to divide both sides by that 0.04 to solve for K. So dividing both sides by 0.04, we get our spring constant K is equal to 2,500 newtons per meter. And that's our answer. All right, last but not least, we're going to talk about kinetic energy. So kinetic energy is the energy of motion, which we've talked about before. So if an object is moving, it has kinetic energy. If an object is at rest, it has no kinetic energy, and that is very important. So the kinetic energy of an object depends on both the mass of the object as well as the object's speed. The equation for kinetic energy that we get is kinetic energy is equal to 1/2 times the mass times the object's speed squared, or velocity squared. In this case, because it's squared, if it's a negative velocity, it just becomes positive. So we get KE equals 1/2 times mass times velocity squared. Remember, kinetic energy is also in joules, just like potential energy. Mass is in kilograms, and then velocity or speed is in meters per second in this case. It's very important. All right, our example number 3, we have a 500 kilogram golf cart has 6,000 joules of kinetic energy. How fast is it going? So again, let's write down our givens first. First and foremost, we know that the golf cart is 500 kilograms. So our first given is that the mass of the golf cart is 500 kilograms. It says that it has 6,000 joules of kinetic energy. So writing that down, we get kinetic energy equals 6,000 joules. And then we want to know how fast it's going. So we want to know what V, the velocity or speed of the golf cart is. So writing down our equation, we get kinetic energy is equal to 1/2 times mass times velocity squared. Plugging in our numbers, we get kinetic energy here is equal to 6,000. Mass of the golf cart is 500, and then V is what we're solving for. So we get 6,000 joules is equal to 1/2 times 500 times V squared. First and foremost, I'm going to multiply both sides of this equation by 2 to get rid of this 1/2. So I get 12,000 is equal to 500 times V squared. I now divide both sides by this 500 in order to get V squared by itself. So I get 12,000 divided by 500 is equal to 24. That's equal to V squared. In order to just solve for V, we have to square root both sides of this equation. So we get the velocity is equal to 4.9 meters per second. All right, and last but not least, so I just taught you about a couple different types of energy and gave you some equations and examples with those equations. So We are next going to talk about this concept called conservation of energy. Now, the rule here is that energy cannot be created or destroyed. It just changes forms when we have a closed system. So, energy can change from one form to another, meaning we can eat an apple and then get energy from that chemical energy and transfer that energy into kinetic energy, so energy of motion. We can put gas in our car, which is chemical, and then our car then can use that energy to transfer that chemical energy into energy of motion or kinetic energy. Radiant energy from the sun can then be transferred into chemical energy in plants. Electrical energy from our outlets can then be transformed into thermal energy in ovens. So energy cannot be created or destroyed, it just changes forms. So you always, when you have a closed system and no work is being done, we have the same amount of energy no matter what. All right. And we'll talk about that more next week when we talk about conservation of energy. All right, everyone. I hope that this was helpful. Let me know if you have any questions. Feel free to email me and make sure that you look up my office hours because I'll be on there for about an hour or so during that office hour so that if you have any questions on the homework, you can ask me then during that office hour. All right. I hope everyone's well and I will see you guys next time.